Hey guys, so in this video we're going to learn about the volume of revolution or the volume of rotation about the x-axis. And in order to understand this, we're going to try solving the following question. The question says, the diagram shows part of the curve y is equal to x cubed plus 1 to the power of 1 half. So here we have part of the curve y is equal to the square root of x cubed plus 1 and the point P that has coordinates 2, 3 lying on the curve. So here we have the point P. Find, showing all necessary working, the volume obtained when the shaded region is rotated through 360 degrees about the x-axis. So what the question is saying over here is, we have the shaded region from x is equal to 0 to x is equal to 2 under the curve. And what's the volume of the shape obtained when this shaded region is rotated about the x-axis? When we rotate the shaded region 360 degrees about the x-axis, we get the following shape over here. And what we want to do over here is we want to find the volume of the shape obtained over here. Now we want to evaluate the exact volume of this shape. And in order to do that, we're going to try and approximate the volume of the shape over here. And we can do that by dividing this shape into a stack of discs that I've shown over here. What we can do is we can find the volume of each of these discs, and then we add up the volumes, and we get an approximate for the volume of the shape. So now to find the total volume of all of these discs, what we can find is the volume of each disc and then add up the volumes. Now what's the volume of each disc? Well, each disc over here is a cylinder. And we know that the volume of a cylinder can be calculated using the expression V is equal to pi r squared h. Here V is the volume, r is the radius, and h is the height of the cylinder. Now if we look at the disc over here, right, each disc has a height of 0.5 units because the shaded region over here is from x is equal to 0 to x is equal to 2. So the length of this region is 2 units and is divided into 4 discs. So each disc has a height of 2 divided by 4. So that's 0.5 units. And the radius of each of these discs is simply the y coordinate on the curve. Or we can say if y is equal to f of x, we can say for the first disc, for example, when x is equal to 0, the value of y on the curve is f of 0. That's the y coordinate. So the radius over here is f of 0. That's simply the y coordinate. When x is equal to 0, the y coordinate is f of 0. Similarly, for the second disc, when x is equal to 0.5, the y coordinate is f of 0.5. So the radius would be f of 0.5 and so on. So then we can calculate the total volume of these discs by using the following expression. The volume of each disc is V is equal to pi r squared h. So for the first disc, the height is 0.5 units and the radius is simply f of 0. That's the y coordinate. So we have pi times the radius, that's f of 0 squared times the height, which is 0.5. For the second disc, when x is equal to 0.5, the radius r is f of 0.5. So we have pi times f of 0.5 squared, that's the radius squared times the height again, which is 0.5. For the third disc, x is equal to 1, so the radius is f of 1. So we have this expression for the volume of the third disc. And for the fourth disc, x is equal to 1.5, so the radius is f of 1.5. And if we add up all of these volumes, we can get the volume as approximately 13.35 units cubed. And we know that this volume over here that we've calculated by adding up the volumes of each of these discs is lesser than the volume of the shape that we want to find. So we can say that this is an underestimate. And it's an underestimate because we're ignoring the volume of these spaces between the boundary of the shape and these discs over here. So we know that the volume of the discs is lesser than the volume of the shape. Now we can get a better estimate for the volume if we divide the shape into a greater number of discs. So over here I've divided the shape into 8 discs instead of 4 discs. And if we add up the volume of each of these discs, the estimate that we get over here is 15.90 units cubed. So that means we're getting a much better estimate. This is still an underestimate because we're still ignoring these spaces over here between the boundary of the shape and the discs, but it's a better estimate than if we had just 4 discs that we were calculating the volume for. So with 4 discs, our estimate is 13.35 units cubed, and with 8 discs, our estimate is 15.90. So we can say over here that if we increase the number of discs, we get a better estimate. Now, if we had n discs over here, the expression that we can use to find the total volume of the n discs is the following. So in the first example, n was equal to 4. In the second example, n is equal to 8. So as we increase n, we get a better estimate. So for this expression over here, if we look at the example given to us, x1 is the center point of the first disk, and the radius is simply f of x1. So the volume of this first disk over here is pi times the radius f of x1 squared times the height delta x. And we know that the height of each of these disks is the same. So the height of each of these disks is delta x. For the second disk, the center point will be x2. So the radius will be f of x2. So again, we have pi r squared h and so on. And if we add up the volume of each of those n disks, we get an estimate for the volume of the shape. Now we can simplify this expression for the volume by factoring out pi over here, since pi is a factor in each of these terms. Now since we want to find the volume of this shape over here, we know to get a better estimate for the volume, we have to increase the number of disks n. So we can say that we can find the volume of this shape over here if we have a very large number of disks. So we can say that as n approaches infinity, so as n gets larger and larger and larger, and is a very large number, we can say that the volume of those disks is equal to the volume of the shape. And we know that as we increase the number of disks, so as n approaches infinity, as n gets larger and larger, the height of each of these disks, delta x, gets smaller and smaller. The greater the number of disks, the smaller the height of each of these disks. So as n approaches infinity, we know that delta x approaches 0. And when this happens, if we have an infinitely large number of disks of infinitesimally small width, of very small width of each of these disks almost being equal to 0, if we add up the volume of all of those disks, we can say that that volume is equal to the volume of the shape over here. And that sum can be represented by the following expression. Here, what we're saying is, since delta x is getting smaller and smaller and smaller, we can say that delta x is just dx. That's a very small change in x. That's almost equal to 0. The radius at any given point x is simply f of x. So we have pi times f of x, the whole thing squared. That's r squared times h, which is dx over here. So this integral over here represents this sum as n approaches infinity, and therefore delta x approaches 0 over here. That's dx, and we factored out the pi over here. So this expression will give us the volume of revolution or rotation for any function 360 degrees about the x-axis. And we're integrating from x is equal to a to x is equal to b. So in the example that we have over here, we're integrating from x is equal to 0 to x is equal to 2. So now let's calculate the exact volume of revolution or rotation about the x-axis. We can say that v is equal to pi times the integral from x is equal to 0 to x is equal to 2, from x is equal to 0 to x is equal to 2 of f of x squared, that's x cubed plus 1 to the power of 1/2, the whole thing squared, with respect to x. And over here, obviously, the powers eliminate each other. Half times 2 is just 1. So what we're doing is we're saying the volume is simply pi times the integral of x cubed plus 1 with respect to x, from x is equal to 0 to x is equal to 2. So then we can say that the volume is equal to pi times the integral of x cubed is, if we increase the power by 1, so we get x to the power of 4, and we divide by the new power, so that's divided by 4, plus the integral of 1 is simply x. We're going to evaluate this integral from x is equal to 0 to x is equal to 2. So first we substitute the upper limit over here, so that is x is equal to 2. So what we get over here is that the volume is equal to pi times x to the power of 4, so that's 2 to the power of 4, that's 16, divided by 4 plus 2. And we're going to subtract whatever we get for the lower limit. However, we can clearly see that when we substitute x is equal to 0, we simply get 0 over here. So then we can say that the volume is equal to 16 divided by 4 is just 4 plus 2. So that's 6 times pi. So the volume is simply 6 pi units cubed. So that is the exact volume of revolution or rotation when this shaded region is rotated about the x-axis. In other words, that's the volume of this shape over here.